IWCS webinar series. We offer this opportunity to see our technical papers once a month. My name is Dave Cadu, and I'm honored to be your CEO and director of IWCS. I will be your moderator for today's event. A few housekeeping items. Please note that as an attendee, you're part of a larger audience. So during the presentation, all participants will remain in silent mode. And also as a reminder, this event is being recorded for rebroadcast and posting on our website and YouTube channel. We encourage you to submit written questions at any time during the presentation, and please use the chat panel on the right of your screen on the IWCS webinar platform that you signed into. After typing your questions in the space at the bottom, hit the send button, and your questions will be addressed as time permits at the end of the presentation. Again, please kindly enter those questions in the chat box on the webinar platform as opposed to the Zoom platform chat. Our IWCS webinar series event is hosted by the Cable and Connectivity Industry Forum. And today, let me transition here. Today, we're honored to have Bulent Kose from Panduit Corp. He is the Principal Optical Engineer located in Illinois, USA. Bulent will be presenting his paper on single mode transmission over OM1 multimode fiber, offset launch versus fundamental mode launch. Bulent Kose is a Principal Optical Engineer in the Fiber Research Department at Panduit Laboratories. Bulent has over 20 years of experience in fiber optics in areas of local area network cabling research and application testing on fiber device development, link simulation, and modeling. Bulent is a member of TIA TR 42.12 and the IEC SC 86A US Technical Advisory Group, and has several technical contributions to TIA TR 42 on optical fiber measurements and specification developments. Prior to joining Panduit, Bulent worked at Nexans on advanced local area network application R&D projects on both fiber and copper. Bulent received his Master of Science in Electrical Engineering from Drexel University and his Bachelor's of Science also in Electrical Engineering from Middle East Technical University in Ankara, Turkey. So thank you, Bulent, for participating, and we welcome you to present at today's IWCS webinar series event.
Thank you, David. Thank you for the kind introduction. Hi, everyone. Hello, good morning, good afternoon, good evening, wherever you are. So this is Bulent Kose from Panduit Corporation. And as David said, introduced, I'm going to talk about our paper from 2021, single mode transmission over OM1 multimode fiber, offset launch versus fundamental mode launch. So I'd like to introduce this topic before I go into some of the measurement results and this technical study that we've done. We've been looking at this for a couple of years in our research lab here at Panduit. So the idea is, as you might have noticed, when you look at the TIA IEC standards for fibers, we're putting OM1 and OM2 fibers as sort of the grandfathered fiber, old fiber, and there's a reason for this because we have these new type of fibers, OM3, OM4, OM5 multimode fibers, where we can have reaches up to we can have a 400 gigabit per second transmission, up to 400 gigabit right now. However, we are all aware that we didn't have these fibers, in the past, and we had OM1 and OM2 multimode fibers with a low and very limited modal bandwidth. And these are the fibers that we used for 100 megabit per second, 100 base FX, or 1 gigabit per second, 1,000 base SX, LX for distances, 100 meter to 2 kilometers. And these are installed in school campuses, government buildings, military facilities, commercial premises. So they do exist. So one of the things we had recognized is that these existing, low bandwidth fibers that has been used now, when the operators are trying to upgrade these for higher speeds, let's say right now for 10 gigabit and above, they come up with a very big question or problem of how to do this. Are they going to replace the cable and put new OM3, OM4, OM5 or single mode fiber, or are they going to, is there another method? So there's a lot of challenges for replacing these cables. First of all, the deployment process itself can be disruptive. Obviously, we're all aware of that, and to ongoing operations. The terrain where the fiber was deployed could be difficult to access. There could be a lot of safety hazards that need to be addressed. And of course, the cost of deploying new optical fiber can be prohibitively expensive. So in this paper, we investigate the performance of an alternative solution of using the existing OM1 multimode fiber using a single mode transceivers and mode field adapters. In the next few slides, I'm going to try to explain to you some of the challenges for doing this. What are the issues? What could be the issues of running single mode over multimode fiber? This idea, of course, is not new. So in the in IEEE, there was a 10 gigabit LRM development where we tried to run single mode over multimode. So this is in standards as well. So idea is not a new idea. So bandwidth of multimode channels depends on the launch condition of the laser to the multimode fiber, the coupling condition from laser to the multimode fiber. And especially for these old fibers, we have some issues, what we call center defects due to manufacturing, variations. In the past, when these, let's say 20, 25 years ago, these OM1 fibers were built, were manufactured, there was more issues. And these days, there's less of these issues due to improvement in manufacturing process in our industry. So in our previous work that we presented to IWCS, we looked at the impact of connector offset, the offset and how it affects mode coupling. And we looked at the impact of that for the single mode transmission over multimode. And I copied here from our slide from that presentation to show that if you have connectors in this, let's say OM1 plant, multimode cabling, or this could be OM2 as well, depending on the offsets that these connectors, of course, the connectors are going to generate some offset at every connection point. It actually increases the likelihood of mode coupling and it degrades our performance. And so we had studied that, and I just put it here. You can go back and look at that paper in IWCS 2020. So we kind of characterized that, the impact of the connectors. So another, again, as I mentioned, 8023 has specified mode conditioning patchboards for offset launch to use single mode over multimode. And this was specifically the 10G base LRM, and also for 1000 base LX as well. But 10G base for 10G base LRM, there was a lot of development trying to figure out how to use these offset launch cords to specifically generate offset, to specifically reduce, the coupling, to increase the coupling to higher order modes, so we can have a more reliable bandwidth, which actually works. So I'm going to show you in this paper that it's more reliable. However, it's very specifically reduces the bandwidth that you could get when you transmit single mode. So another area of concern or challenge for single mode or multi-mode is the mode coupling due to the connectors and any offsets create increases the noise because this is phase sensitive, because when this is called multi-path interference, by the way, MPI. When higher order mode goes into couples into the lower order mode, that creates interference that impacts the performance. So this is a big challenge, and that's why this is one of the results of the connector offset impacting the performance. So as an alternative, as I said at the beginning, the introduction, as an alternative, a low model crosstalk mode field adapter to improve the launch to lowest order mode or the fundamental mode, it can improve the performance drastically. And this has been done. And the idea is, if we replace the connectors in the scenario, if we use a mode adapter at the beginning from single mode to multi-mode, we use a mode adapter. And then if we get rid of all the connectors by fusion splicing them, which means we're reducing all the the offsets that could impact, that could generate mode coupling, then we can have a pretty reliable system that works single mode over multi-mode over longer distances. And this is, so I put here this picture again from one of our earlier papers. This is kind of like a typical deployment of these mode adapters, where in a main distribution frame, you put your mode adapter after the single mode patch cord. So basically you have a equipment transceiver, single mode transceiver, let's say 10G base LR or even 10G base LRM, which is the one that I use in my test, which is kind of like the worst case. And then from the single mode, you have this mode adapter, and basically everything else is spliced throughout the OM1, let's say 6.5 micron OM1 multimode infrastructure. And then at the receive side, depending on the length of your infrastructure, you could use another one of these mode field adapters, which improves more. Or if the length is not very long, let's say less than 800 meters or 500 meters or so, you may just go without the second mode adapter, and then and then after that you can splice single mode patch cords and stuff. So it works quite well. So the idea is, can we assure legacy installed OM1 cable performance with single mode transmission using OM1 fibers? So that's the question that we're raising. In this work, we try to answer this question by testing a series of worst case OM1 multimode fibers with single mode transceivers with mode field adapters to improve the link performance. So in the next couple of slides, I'm going to talk about these fibers that we looked at, OM1 fibers, and how we characterize them, and then I'll show you that we found some good and worst case performance of these fibers to actually look at the bit error rate performance. So the first thing that we've done is we looked at a overfilled model bandwidth of these fibers. We got about 20 OM1 spools from a couple of different vendors. And these were requested to be worst case at 1300, which is by standard minimum of 500 megahertz kilometer overfill bandwidth. And we measured 10 of these fibers, using the setup that I show here. So we have a supercontinuum source with a single mode fiber coming out of it, and then we have a monochromator, and we launch into the multimode fiber. And we use a mode conditioner to make sure that we launch into all of the modes. We overfill the modes of the multimode fiber, and then the next is our device under test. The length, depending on. Actually, we looked at about 100, 200, or 300 range of lengths of these fibers. And so our source is a 6 picoseconds pulse supercontinuum source, which is about 7 nanometer full width, half maximum spectral width. And again, the overfill condition is created using this mode conditioner in the setup. So here is some graphs that show our measurements results. In the upper section, you see, I'm showing here 10 of these fibers, as I mentioned. We see the temporal pulses that are measured at each wavelength. And again, these pulses are just single pulses. It's not like differential mode delay measurement. We're not offsetting, which actually I did also for some of these fibers. But in this measurement, it's overfilling the fiber in terms of mode overfilling, and then sending the signal, the 6 picosecond pulse. And basically, you could tell that the fibers, they have, and then at the lower graph, at the bottom, I show the OFL bandwidth that's calculated from above measurements. Basically, the calculation, we've done it similar to DMD, sort of the de-embedding calculation, using a reference pulse, and then using, basically it's a frequency domain sort of calculation. And as you could tell, so I actually noted with red circles here, I noted the 500 megahertz kilometer. And as you could tell, some of these fibers were, yes, they were right around the worst case, so they were like worst case. But some fibers, the fiber F1 and F2, especially F1, which this F1, you'll see more of this, studied, in the paper, had significantly lower modal bandwidth than 500 megahertz kilometer. So this is something that I wanted to mention at this point is, yes, when you purchase, let's say you're going to purchase OM1 fiber, and most probably as the user, you're not going to measure its bandwidth, and most probably it will have enough bandwidth. It will be compliant. However, due to the manufacturing variations of these, the length variation, which we studied carefully in our lab here at Panduit. And this happens in all the manufacturing techniques. There's variability along the length. Some sections of this fiber could have a low overfill bandwidth. So this fiber, although let's say the F1 fiber, although it looks like it's non-compliant, it doesn't mean that it doesn't exist. And as a matter of fact, this fiber is something that we just purchased from one of the vendors, and they had this fiber as an OM1 fiber that they were selling. So it is possible that it exists. And for us, it sort of represents a sort of good worst case fiber to understand, performance, the worst case performance for single mode over multimode. So in this slide, I see a little more detail on some of these fibers. In this slide, what we've done is we actually looked at, we did a measurement that's similar to a DMD measure. It's basically a differential mode delay measurement. And this is done at 1310. So we're able to do this using our supercontinuum source again, set at 1310 nanometer using the monochromator. Let's see. Okay, yeah, so here's one of the things I wanted to point out is some of these fibers like F1 and F2, and also a little bit on F5. You see, I actually focused here the zero offset when the single mode is centered at the, let's say, at the zero offset of the multimode at the launch. You see that there's not just one pulse, and there's a secondary pulse, which means that at the zero offset, and a higher order mode is being, or mode group is being excited. And this is important. And this actually is something that's something we call center defect impact. And this happens in OM3 fibers, OM4 fibers as well. I guess OM3 fibers, OM2, OM3 fibers mostly. And it's a defect that happens during the manufacturing process, that the the refractive index of the center is not very smooth. There's some defect there, and it causes this. So the way this can show up in actual performance is if you don't use a mode field adapter, and if you just launch from a single mode to this particular fiber, this secondary mode will be excited. And actually, you're going to find out that in our measurements that we showed that. Actually, yeah, in this setup, I'm going to try to show that. So impact of mode field adapter for single mode to multi-mode fiber launch. So what we've done is we looked at those the center. We looked at the temporal pulse at 0 offset with different conditions. One is just go from single mode splice to the multi-mode. Second is using a mode conditioning patch cord. That's the standard, IEEE standard sort of mode conditioning patch cord, which I'm also going to explain a little bit in a few slides later. And the other one is using this fundamental mode, the mode field adapter. So here is the results. Again, I'm focusing on the worst case F1 fiber, F2, and the F5 fiber in those fiber list. So as you can see again, for the F1 fiber, when single mode fiber is spliced, actually I said there are two graphs here, offset and spliced. Offset means it wasn't spliced, and then I spliced it. They're about the same. So when single mode fiber is spliced, you see the secondary peak. But on the same setup, when I use the mode field adapter instead of the single mode fiber direct splice, mode field adapter actually removed the launch or coupling into that higher order mode. Basically, mode field adapter, regardless of how the fiber's refractive index looked like, the mode field adapter was able to get rid of coupling into that higher order mode. So I was able to couple into just the fundamental mode using the mode field adapter. And in the last part, and I actually did this for two mode field adapters from two vendors. So they work quite well, both of them. In the last section here, I show the same experiment using the 10G base LRM offset launch, the mode conditioning patch cord. Again, as I mentioned, the idea of the mode conditioning patch cord is to try to couple into middle mode groups, which is of course in the case of OM1 fiber, there is hundreds of modes, or there's a very high number of mode groups, I would say. I think the mode group number is 9. There's 19 mode groups for 50 microns. So for 62.5 micron, there should be around maybe 20, 30 or something. I don't recall exactly the number right now. But anyway, so it launches into a large number of mode groups when you use the offset launch. And I'm going to talk about this briefly later. So again, F2 and F5 fibers, very similar. If you don't use the mode field adapter, you see the secondary peaks in the upper and the lower. If you use the mode field adapter, it kind of gets rid of that. So this is telling us that this mode field adapters, both of them mode field adapters, 1 and 2, they seem to be cleaning this higher order mode launch. Okay, so a caution on commercial mode conditioning patch cords. Oh, so this is interesting, because when I purchased mode conditioning patch cords from just off the shelf from some vendors, what I found out was they look different, and they look quite different, very significantly different. And so to explain what the difference is in just a few minutes, I wanted to show here. I have some excerpts here from standards, and from a 8023 AQ LRM requirement and 1000 base LX requirement, 8023Z requirement. So there is a requirement for coupled power ratio, and this is for both. And then for 10G base LRM, there is also an alternative launch. That's the requirement. Coupled power ratio is the requirement for mode conditioning patch cord, but there's also an alternative launch that's specified in these, that only looks at the encircle flux. So when I plot the encircle flux, when I measured the coupled power ratio, mode conditioner patch cord 1 was compliant because it's supposed to be between 28 and 40 dB CPR. But mode conditioning patch cord 2 and 3, they were very underfilled compared to this, 1.5 and 3. And then I looked at their encircle flux and I found out that they actually designed this according to this alternative launch, which is incorrect. Because if you do this, the idea of the alternative launch is that you don't have to create overfilled launch or mid-order launch because you rely on your fiber that if your launch single mode is going to work. Obviously, that kind of beats the purpose because you know that if the fiber, if you know your, you know that it's very difficult to know exactly your fiber. I guess that's the point I'm trying to make, and that's why there is a risk of just putting single mode or this OM1 fiber because it may or may not work depending on the coupling. So in this last section, I will talk about our measurements for bit error rate to clarify these differences between the launch conditions and the best and the worst case fiber that I mentioned. So for the setup, basically I have the transceivers. I use the 10 gigabit LRM, 10 G-base LRM transceivers, and these are sort of worst case. These are fiber pro based, around 13, 10 nanometer spectral wavelength. And of course, this is LRM, so the receiver is a linear receiver. And of course, I'm not using EDC in my setup because these SFP plus transceivers, they don't have the EDC. EDC is supposed to be in the host system. So I have three conditions that I used to compare against each other. One is directly splicing with single mode. The other one is using mode conditioning patch cord. Actually, in this case, I'm using the IEEE compliant one with the high CPR value, the 39 dB CPR. And the third launch condition is, of course, the fundamental mode launch using two mode field adapters. So I use a polarization controller, atomized transceiver, and a fiber shaker between the output of my launch and at the beginning of the OM1 DUT, so that I can generate variability, because I know that the key about this single mode over multimode is variability. You know, maybe the rotation of the fiber can have some impact and things like this. And I have an attenuator to do a bit error rate performance test. And so this is basically the results for two fibers, the F1 fiber, which was the worst case fiber, like very low in overfilled model bandwidth, and the F3 fiber, which had the best model fit bandwidth, overfilled bandwidth at 1300. So if you look at the 50 meters of F1 fiber, you basically what we're seeing is mode field adapter 1, adapter 2, they perform quite well. And also I see here a offset patch cord performance as well, because this is a very short fiber. So what happens is when you launch into all the modes, high order modes, you basically utilize all of the bandwidth. And of course, this fiber has a very low model bandwidth. So, but at 50 meters, that corresponds to a good performance. So we can see that it actually works. But the same mode conditioning patch cord disappears. There's no link when I increase the length to 100 meter and of course 400 meter as well. And I didn't do that in the F5 fiber result here, because I didn't look at 50 meters, very short length. I only looked at 40 and a kilometer of this other, the better fiber. So basically, in terms of the mode conditioning patch cord, the standard mode conditioning patch cord, it scales with length. Like when you have, you know, the bandwidth is you know, it's just like bandwidth length scale of normal fiber with let's say overfilled condition. So it scales with length, and when you increase the length, you don't have a link anymore. So for so the green is direct single mode. Basically, I just splice single mode. And what's interesting in this one is even for very short length, direct single mode for this test, didn't have a good performance. And for 100 meter, it didn't have a good performance. And for 400 meter, it really didn't matter. It's about the same performance. And so that's the part. So this actually was, excuse me, this was sort of good to show that, excuse me, good to show that yes, single mode directly, like if you don't use connectors, of course, is better. If you just splice single mode, it might work. Sometimes it works, but it's not reliable because even that splice, even if you use a splice, you will, first of all, you will couple in higher order modes, as I mentioned before, in those, the zero offset measurement for the temporal pulse. But sometimes there may be good coupling, and then there's less coupling into that higher order mode, and sometimes there's more coupling, so it's not reliable. But if you use the mode field adapter, it's always reliable. Basically, you get always good performance when you use mode field adapter, even with this very, very bad, performing fiber. So you can look here, mode field adapter 1 really pretty much didn't change. Mode field adapter 2, it got a little worse for 400 meters. And I didn't really look into this exactly why, but it could be that maybe there was maybe the splice that I did has some impact on it. So it could be something. But again, in general, its performance with the mode field adapter is much better. So for the F3 fiber, the good fibers, basically mode field adapters work again very, very well, very close to, for 440 meter, the performance was very close to ideal performance for back-to-back. But also the direct single mode splice wasn't very bad either. So this tells you, yes, if you just splice single mode, it may work, but it's not reliable. You cannot just rely on it because it depends on the fiber. And again, like the fibers that we looked at here is quite a variation of 1310 model bandwidths performance. And other than these two fibers, I had bit error rate performance similar to this on a few of the other fibers, which I didn't put in the paper, and I actually didn't put in this presentation either. And all those results indicate the same behavior, that you get consistently better results with the mode field adapters because of cleaning those higher order mode launch at the beginning. So to summarize this, and give you the conclusion of this, again, the use of single mode transceivers for transmission over multimode fiber can provide significant advantages in brownfield fiber network upgrades that I mentioned at the beginning, that introduction. And there's a standard-based solution for using existing OM1 fiber plants for 10 gig transmission, which is the 10G base LRM, but it requires using mode conditioning patch cords with electronic dispersion compensation. And the link reaches are limited to 220 meters. And in this study, we study model bandwidth of OM1 multimode fibers, and we identify an OM1 fiber to represent worst case install base OM1. That was the F1 fiber. And so this helped us to understand better the performance or single mode over MMF. We use this worst case fiber to study channel performance impact when low model crosstalk mode field adapters are used for single mode to multi-mode launch. Our measurements indicate that fundamental mode launch using mode field adapters outperforms all other launch conditions, and it is the best option to upgrade legacy OM1 multi-mode fiber cable plant to speeds or 10 gigabits and beyond. So that's my presentation, and I'm now it's open for any questions from the audience, and I'd like to just try to see if I can address those.
Yeah, thank you so much, Bulent. Again, an excellent presentation and important information as these technologies evolve for MMF. I invite the audience to enter your questions that you have for Bulent in the chat for the webinar platform. In your presentation, Bulent, you mentioned that a center defect can result in coupling of other modes than the primary mode in single mode launch. Is this defect principally due to artifacts such as the core rod in OVD fiber production?
Yes, I mean, I think that's one of the reasons, but I believe I've seen personally these defects happen, at different degree in different manufacturing styles as well. But OVD, I think, is the one that happens the most.
Okay. In terms of cost, could you compare MFA and fundamental mode launch solutions?
I don't have cost information, but definitely there is definitely there's a price for using the multimode, the mode field adapters, because this is, I mean, this is a component that you have to add in your installation. Yes, I don't have the cost information. Sorry. I mean, yeah, for that I'm gonna have to do offline.
Very good. And again, I'll provide the contact points for Bulent if you wish to reach out to him directly. Are there any more questions? Taking a look in the chat, I don't see additional questions. Here's one. Any idea how multimode fiber connector offset affects the performance?
Yes, so that's a good question. And actually, we, like, as I put in one of my slides, we had presented this effect in 2020 IWCS specifically. We, let me see here. Yeah, here. Actually, we did have a modeling, and we also supported this with experimental data. So in this graph here on the left, we have this parameter m minus 10 log p, p group, pg or pt. So that's the group power versus total power of the modes, mode group power, the Gth mode group versus total power, total, mode group power. And so we plotted this as a function of the offset, and offset obviously is the parameter of the connector. And then we kind of we plotted how this is going to impair the eye diagram and the performance, of course. So we have this as another paper. Again, I encourage you to look at that paper from 2020.
Good. Okay, I'm looking. What is the maximum achievable reach, Bulent?
Yes. So if you use two of these mode field adapters at the beginning and at the end, you could go to a couple of kilometers. And actually, there is one of the vendors reported to us, one of the vendors of these mode field adapters, that they had actual working lengths in the range of 6 kilometers for 10 gigabits. So they could go quite long distance. But I would say it depends on the quality of that fiber. And again, this my fiber, the F1 fiber, is kind of like our I guess the worst case gold standard, I would say. So if you have that fiber, maybe you're not going to be able to reach 6 kilometers. But you could go to, like, if you use two of these modules at the beginning and end, you could go a couple of kilometers over 10 gigabit per second, and you can scale this for, of course, for 40 gig, for 4 times 10, it'll be about the same. But if you go to 10 gigabit and above, you're going to have to scale the reach. Very
good. Okay. Seeing no more questions, we'll keep an eye out if anyone has a last minute question for Bulent. But meanwhile, again, I'd like to thank Bulent for presenting this very important and interesting topic today. Please note the contact points being shown should you wish to contact Bulent after today's event. Each of these IWCS webinar series of presentations are recorded and will be archived on the IWCS.org website. It normally takes a week or so to get these posted. The IWCS webinar series will continue to conduct technical paper presentation webinars and separately sponsored company events several times each month. Our next scheduled technical paper presentation webinar will be on Friday, June the 17th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event. Please feel free to share those announcements with your colleagues so that they can join in and register as well. With that, before I close and wrap up, Becky, any last minute questions that you might see?
No, I don't see any final questions. Thanks, Dave.
Very good. Okay, it is important that we all recognize and thank our IWCS partner sponsors who contribute greatly to the success of our Cable and Connectivity Industry Forum. Without their leadership, their generosity, we would not be able to bring these important technical innovations and information to you and our global community. Again, thank you to these leading suppliers in our industry and for your support. With perseverance and confidence, our next 71st annual Cable and Connectivity Industry Forum will now take place live on Monday through Thursday, October 10th through the 13th, 2022 at the Rhode Island Convention Center in Providence, Rhode Island, USA. Please watch your inbox, your social media, and our website to learn more about the program. We've just recently put together the technical content and other aspects of the program. So be on the lookout for that as the information becomes available. Again, visit our IWCS.org website for more event details. So with that, again, Bulent, many thanks for your help and support today, and for all of our audience for your participation. And this concludes today's webinar event.
Thank you.
Have a great weekend, everyone.
Thanks.